All right, good morning again. And so this is the reaction that is very important when we want to make pretty much an alcohol, avoiding the use of water as acidic water like H plus, H2O or H3O plus, which is the same thing. So we use a reaction that is called an oxymercuration-demercuration. Now in this reaction, the important step is the use of mercury acetate. So mercury acetate, and we're going to start the mechanism from this side. Under the reaction conditions, pretty much dissociates into two things. So the bond between mercury, which very importantly has a lone pair, and one of the oxygen breaks, and it gives us two kind of compounds. We get an acetate, which will not participate in the reaction, plus it will give us our actual electrophile, which is this mercurinium ion. This is the electrophile. Okay, so this is the one that is going to react with our alkene. Now, as usual, I'm going to draw the alkene as a Lewis kind of structure because I want to see what's going on around the double bond. The substrate would normally be subject to rearrangement. So this is going to react with the mercury acetate, this ion, and this is how the reaction goes. There are no rearrangements, so a new kind of intermediate forms. So the alkene, as usual, will attack the electrophile. But what was discovered because of the products that were obtained without any kind of rearrangements is somehow the carbocation doesn't form. That is because before the carbocation forms, the mercury attacks the other carbon. Now, I'm going to show you some stereochemistry because the attack happens on the same face of the double bond, which means it's a syn attack. So I'm going to arbitrarily draw one of the possibilities. So I'm going to put the mercury, as you'll see in a second, into wedges. So we're going to draw the new bonds being formed as wedges here and here. And the mercury is going to have a positive charge because still has 3 valence electrons, still be bonded to the acetoxy group. Next step is the other one that is very important. So now the nucleophile comes in, and the nucleophile is water. Now, when reacting alkenes with a variety of reagents, you always are going to form these 3-member ring intermediates that are going to have a positive charge on one of the elements. So the water now comes in and is going to open up this 3-member ring. It is very important to understand that the water is going to attack, or the nucleophile in general, is going to attack the carbon that is more branched. And the bond between that carbon and mercury is going to break up. Now you might ask, but why does it attack the most hindered carbon? Well, this is because in these kind of structures, the bond between the carbon and the mercury, the carbon that is more hindered than the mercury, is actually longer. And that makes that bond weaker, and the carbon have a more delta plus, so partial positive charge with respect to the other one. So this will give us an intermediate. This is going to look like this. The attack happens from the back, so it's going to be a backside attack. So this is the part of the molecule that did not react. So the mercury is going to be on a wedge. It's going to have a lone pair. now is neutral, but the water that came in now is going to be on dash. So the stereochemistry of the carbon will change. So we end up with OH2. One of the lone pairs is still there. This oxygen is actually positive. So we have 2 more steps to get to the final product. The first one is going to be deprotonating this intermediate to make the product of the so-called oxymercuration, which is the first step. So water takes the hydrogen, so this again the part of the molecule that did not react. Now we have mercury with this group attached, and on the other carbon we have water. Plus, obviously, we have H3O plus. So this reaction is called an oxymercuration, which is making this compound, and then there's a demercuration step. Now the demercuration is done using a reducing agent. That would be sodium borohydride, NaBH4. The sodium borohydride is basically a hydride donor, so it's equivalent to NH-. This reaction is a redox radical reaction. You don't have to show a mechanism for this step. All you have to know is that the mercury with these acetoxy groups gets replaced by a hydrogen. So you can simply draw it out. Now keep the stereochemistry in place, even though you might not form chiral centers sometimes, mainly because you want to show that you can explain why the addition is actually a so-called anti-addition, which is kind of happening on opposite sides. So the OH will be on one side of the molecule, the hydrogen is on the other side. This is your final product. So the oxymercuration-demercuration product is basically, again, an alcohol, but is the product that we would expect while doing a regular hydration without any rearrangements. So it's a very important reaction, it's very commonly used to make these kind of reactions. The addition is a Markovnikov type of addition, because if you look at the final product, the hydrogen was added to the carbon, they had more hydrogens to begin with, and the OH goes onto the carbon that was more substituted. Please make sure that you redraw the molecules. If they're given to you in a line angle type of format, draw them in the way I did, because that way you can see every single kind of bond. And so this ends this kind of mechanism. The next mechanism is going to be the hydroboration oxidation.